Calculus BC 4.7 on optimization. We're dealing with our last example, example 3. And this is a problem where we're really going to review quite a bit. Y squared equals 2x is a sideways parabola. It's a parabola that opens actually to the right. If you let x equal 0, you'd see that y was equal to 0. If you'd let x equal 2, for example, 2 times 2 is 4, y squared would equal 4, y could equal plus or minus 2. So you could quickly see that we have a parabola opening towards the right. When y squared is equal to something positive, we open up towards the right. But we'd like to find the point on this parabola, sideways parabola, that is closest to the point 1, 4. Now 1, 4, you can hopefully confirm immediately that this point is not on your parabola. If you were to let x equal 1, it's pretty clear that y would not equal 4 in this equation. What we're asked to do, though, is we're trying to find the point on this parabola. Maybe it's over here, who knows where this x comma y is actually going to be closest to the point 1, 4. So you might not be too surprised that we're going to be using the distance formula in this problem. So the distance formula, really the Pythagorean theorem in disguise, is x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And of course we have some points. The first point maybe we were thinking about was 1, 4. But here's this arbitrary point that I've written in red. It's the point that's truly on the parabola. We could call that x2, y2. So, as we try to put this together, x2 I'll just call x. Here's x minus 1 quantity squared. Plus over here our y2 is just a y minus our y1, which happens to equal 4. And my word, as you begin to wrestle with this, as you're beginning to really think through this, it doesn't take you too long to realize, my goodness, this problem has 3 different variables that are changing. Depending on what point you're choosing on this parabola, your x and y coordinates are going to change. The distance d is going to change just as well. So my word, is we're trying to find a way to maybe get a link here. Take a look at the y squared equals 2x, though. If I were to solve, say, for x, I could then substitute in, and I could say, you know what, I can get this down, thank goodness, to just 2 variables. And that, honestly, is your ultimate goal when you're optimizing. You don't want to have 3 or 4 variables that are changing. That's really getting into Calc 3, multivariable calculus. And right now I have an equation where I could optimize distance d. However, I do think that it's pretty clear that taking a derivative on that right-hand side would get brutally ugly. There's a reason why I want to show you this example. It's because this does show up regularly enough that this really cool feature can help you out. I'm going to consider d squared. If I were to square d squared, or square d right here, I would get such an easier equation to work with. You can see right there. And at this point, I'm going to let capital D equal d squared. So what I've just done, and this can seem to be a little bit different is I've changed the problem. And here's the thing. I'm trying to find a closest point. I'd like to find d, little d, to be as small as possible. Take it on good faith right now that when little d is as small as it can be, then d squared, which happens to be big D, which we're just writing here, will also be as small as it can be. Realize if you take a small number, think of it this way, a small number like maybe d could equal 1/10. Look at this, if you were to square that, you even get smaller still. So take a small number and you square it, you're going to have a square that would be as small as possible. So what are we doing? We're reconfiguring this problem to say, let's optimize capital D. And the reason for doing that is the derivative will be so much easier to work with. Let's do that together right now. D prime, I'm going to need the chain rule. I'm going to bring down a 2. I have y squared all over 2 minus 1 to the 1 power now. But the chain rule, take the derivative of the inside. Down comes a 2. You really have 2y all over 2. You can see that's going to cancel out. And hey, that's going to work out pretty nicely. Take your derivative here. You can bring down your 2. Here's 2 times y minus 4 up to the 1 power. Derivative of the inside is just a 1. Well, I hope you can see pretty clearly that this 2 and this y are going to get distributed. It's as if we have a 2y times y squared over 2 minus 1. And right here, of course, you can start distributing your 2 also. But what are we going to come up with? Well, the 2's cancel out here. You'd be left with y to the 3rd. 2y times a minus 1, you get a minus 2y. And before too long, you can see that this is your d prime. Wow, look at that. So d prime is equal to y to the 3rd minus 8. And when we're optimizing, we're going to find our critical numbers. We'd like to know when the derivative is 0 or when it's undefined. It's not going to take you too long to take a cube root and to see that y would equal 2. There's only one critical number at play. So I'm going to do a number line test, just like we were doing with the first derivative. And, maybe I could test y equals 0, maybe test y equals 3. And of course, I'm testing it into d prime. Plug in a 0, 0 cubed minus 8, you get something negative. That means capital D is decreasing. That also means little d is decreasing, if you think about it. Plug in a 3, 3 cubed is 27, 27 minus 8. You don't even have to know what the particular answer is, just as long as you know it's something positive. So what do we have? We know at this point that there is a local min at y equals 2 because d prime changes from negative to positive. So you found the y coordinate that would minimize capital D. That is the y coordinate that will also minimize little d. The original question was, could you find the point that is closest, that would have d, that distance, being the smallest? Well, remember what's happening. We've got y squared is equal to 2x. So if y were to equal 2, plug that in, 2 squared is a 4. It only takes you a moment to see that x is equal to 2. So the closest point, you need an x value of 2, a y value of 2. So the closest point is 2, 2. If you wanted to find what the minimum distance was, you'd go back up right here to this red block and plug in a y value of 2, and you could find out just how small that minimum distance is. But they didn't even ask for that. They just want the minimum point.